otherwise it will be disaster for us. We will not go there. We will find acceleration at point B first. So we set up, look at there, we set up the same equation, AB equals acceleration at point A plus acceleration B relative to A, one equation, and that other equation is acceleration at point D plus acceleration B relative to D. Clear? And then I equalize these two equations, I put this beautiful equation here. And then AA, I split into normal and tangential, our ABA normal and tangential, and our AD, I put it here, and then I ABD normal and tangential, and here we have a problem. Hey, have a look very carefully. In your diagram, only given our velocity BD, 254 millimeter per second. Does it say about AD anything? Any information about it? Young people? Any information about AD? No. So therefore we assume our BD is constant. Our BD is constant. If our BD is constant, then our AD will be 0. Otherwise, AD must be given to us. Because AD does not have a normal component. Because it is a translational motion, stellar motion. So therefore, our AD disappear. AD disappear. So now have a look, young people. Have a look. All the normal component I wrote here exactly the same way as we did before. We know. And then our AAT is 0 because here no alpha is given here. Because omega 2 is constant. Look at here. Alpha 2 is 0 also written here. So therefore our AAT will not be here. And now I also wrote all these things for you. Look at here. AAN is directed from A to O. Look at there. Can you see that I showed you the direction? And your AAT is 0, 90 degree angle. We don't have it. ABA normal directed from B towards A, and ABAT perpendicular to AB. And our AD is gone. Our ABT directed from B towards D. It is rotating in relation to point D. And our AB tangential is perpendicular to BD. That's all. And our normal component, all we know, we now need to plot a vector polygon. We need to plot our vector polygon. And the vector polygon we'll be doing in the next slide. What is that? Okay? Don't worry about it, because acceleration part is always multiple links because it has a double parameter. That's why it is more crowded than vector polygon of the velocity. So look at here. The first thing we are plotting. Look at very carefully. Don't worry about other line. You only focus on your equation which is telling you to look at. So our first equation is AAN. Our AAN is from the origin. Origin is here. Origin is here. Can you see the origin? Origin is here. And our AAN is directed from A towards O. That's why this beautiful line, and using a scale, we write our AAN parallel to A to O, which equals our absolute AA because our AAT equals 0. That's why. Right? We left up to that point. And then we have another parameter, ABAN. So ABAN, where our AAN finished, unfortunately we don't have AAT, that's why where it finished, it should start this one. It will take the position of AT now. So ABAN directed from B towards A, and that's exactly one thing I am doing here. I am directing parallel B to A from here. This beautiful line, don't worry about other line. This line is our ABAN parallel to B to A. Can you see that? Okay. So where our ABAN finished, our ABAT 90 degree angle of AB, like that, it will start from the tip of where our ABAN finished. Clear? And this dotted line I draw because our ABAT can go this way or it can go downward. So as I am not familiar with that, so what I did, I draw a dotted line passing through the tip of our ABAN. It is going all the way up to that point. Unfortunately, my paper finished, so that's why I didn't contribute. Clear? But still you can see dot line. Okay, I finished the left hand side. And then now right hand side. Aha, right hand side we have a big problem. What is the problem? Our right hand side we do not have our AD. AD equals 0 and AD has a connection with ground. The link of our link 5 D pistons, it has a connection with ground. And it has its acceleration should start from the origin. Should. And also it has a 1 letter index, AD. But unfortunately our AD is 0. So now our ABD on the right hand side, it lost its mother. It lost its mother. Its mother is our AD or father. So hey young people, when my father died, I took all the responsibility of my family because I am the eldest son. Naturally, when it lost this other parameter, parent parameter, then that position will take this subsequent parameter. Clear now? So our ABDN will start from the tip of origin. From the origin it will start. And now you can say, Professor Firoz, you use direction case, you use the word must. Magnitude case of the normal component, you also used word must. But all other location, you all the time say should. Should. If I use the word must, can this parameter take the position of AD? No. That is the little language thing. Is it clear to everyone now? That sort of situation you will find not all the time. All the time, follow the grammar as we did in our previous problem. There are some exclusion. It can happen. But logically, as it lost this parent parameter, which is our AD, so therefore subsequent parameter BBD will be taking its position where it's supposed to start from AD. Clear? If AD was, then AD will start from the tip first. And then our ABD normal and ABDT subsequently follow. Clear? And that's why young people, I did not use the word when I say the links that have connection with ground, their velocity and acceleration should start from the origin of the vector polygon. I did not use the word must. Is it clear? I left a little bit of room for negotiation. Is it clear? And I also said another thing, that all parameters, velocity and acceleration, which have 1 letter index, AD, AB, AA, BD, BA, BB, BC, all 1 letter index also should start from the origin of the vector polygon. I did not say the word must. I only said 2 situations. One is direction of all parameter must be known for graphical method when we construct the vector polygon, and the normal component magnitude must be known to us. The values must be known to us. That's the things I said must. All other places I said should. And now it allows me to start my BBD, our BBD, to start from the origin. So what I did, look at here. I started from here, the BBD parallel from B to D, and this one, and when our BBD finished, our tangential component will be 90-degree angle. I draw it here. And therefore, look at here, young people. This is our ABDT tangential, and this is our ABA tangential. But these 2 beautiful lines intersect, that is our bingo. That is our bingo. So what we did, that is our look at here, ABD normal, ABD tangential, and from origin the diagonal is our absolute ABD, which is equals our AB. Look at here, AB equals AD plus ABD. But our AD is 0, so therefore ABD equals ABD. We are correct. On the other hand, our this one, look at here. This one is our AA. This is our AA. Look at here. This is our AA, absolute AA. And this one is our ABA normal. And this is our ABA tangential. So when we draw a dot, this one, that is our ABA. So this is our absolute AA. This is our absolute relative ABA. Diagonal of this one, our absolute AB, which is our first equation. We plotted everything correctly. And now is your point C. You do exactly the same approach, young people. You set up two equations. Our AC equals acceleration at point A plus acceleration C relative to A, and one equation. And other equation would be AC equals acceleration at point B plus acceleration C relative to B. That's all. And the normal component of AC and normal will be directed from C towards A, and normal component ACB will be directed from C towards B. And the tangential component will be 90-degree angle of their respectively. Nothing else. You plot. So what we did? Look at here. I did not do any magic. I wrote the equation, eliminated, because our AC is neither perpendicular nor parallel to any of the links, so we cannot have in our equation. Direction must be known. So therefore, I did. Now look at here in this one, our AA. What is our AA? This beautiful line is our AA, absolute. And where our AA finished, our ACA normal will start. ACA normal will start. And that ACA is directed from C towards A, and that beautiful line is our ACA normal. Can you see that? This one. This is our AA, and this is our ACA. Parallel to C to A. And we know its value, normal component. So therefore we continue slab. And then where our ACA finish, our ACB tangential will start perpendicular to AC. So this red dotted line, look at here, this red dotted line, look at here, this red dotted line passing through ACAN, it can go upward or it can go downward. So I draw a big dotted line, look at there, perpendicular to AC. I left hand side, and then I moved to right hand side. The right hand side we have our AB. Where is our AB? Our AB is this one, this line. So our at that point is our AB, that entire line from O up to that point. And where our AB finished, that ACB normal will be starting from that point. And how it is directed? From C towards B. And look at here. From here it is directed ACB normal this way, directed from C towards B. So that's why I'm showing you that line. Beautiful, this line. Can you see that? And we know its value because normal component. That's why continuous line. It is not a dotted line. And then ACB tangential, this one, will be 90-degree angle of BC, like that. In another word, it will be 90-degree angle on ACB normal. So this beautiful line is our ACB tangential. Can you see that? So this dotted line and the other dotted line, this one, where intersect, that point from origin, you connect that is your beautiful AC. And this is your ACB normal, ACA normal, and the ACA tangential. From here, the diagonal is your absolute relative ACA. Again, I do it. Look at here, how I did it. ACA normal, this one is ACA normal, and from here up to that point is your ACA tangential. So therefore, diagonal of these two vectors will be your absolute relative ACA. And this one, look at here, this one is your ACB normal, and from here up to that point is your ACB tangential. So therefore, from here, if you draw a diagonal up to that point, that will be your ACB, absolute relative ACB. Is it clear? So please, at home, you go through this, and it will give you a great help. So now, quickly, I spend maybe another 2, 3, 5 minutes, and then we finish. Okay, that give me. So with this note, we stop for our acceleration part. Clear? And I hope you will be able to. Now, young man, if you want to go, you go. Okay. So So I'll be uploading when I go to the hotel these things to you in your canvas. As you found the part 1 yesterday we did, it is already available there. Friends, this one will be available tonight. Clear? So you don't need to, you just print color. Don't put in your mobile phone. Mobile phone you will not learn anything. I don't know about you young people. I find great difficulties to see even myself. Even when I look at it in computer, I'm confused which line, which way is going. Even knowing all these things. So now, quickly, just give me 1 or 2, 3 minutes. We need to start our next topic to give you a preamble, and then we'll go home. And we'll finish tomorrow. Now, young people, tomorrow, look at here how I did. From the vector polygon, all the line, you measure, multiply with the scale, you get the value. And then, of course, now I wrote all the angular acceleration, how we find. You see all these things are written. And take the same approach. Same approach, young people. And then, one thing I did not tell you, you can do it at home. Our main objective is every link to find out the mass center, the absolute acceleration. Clear to everyone? So, for you, I will upload everything together. You look at how I did in the vector polygon. You don't need to do extra work. You can find all of them from the vector polygon, how I found the mass center one of each of the link. I'm talking about the moving link. The link that doesn't have a motion, we are not talking about that. So you look at that, and I also wrote exactly the same thing, so it will give you a little bit of understanding that why we need to know the acceleration not only at joint point, we need to know each link's mass center so that we can balance it. Because if we know the acceleration at the mass center, that acceleration we multiply with the mass, that link mass, then we know the dynamic force which is shaking. And we also know the direction of AG, so we know which way the shaking force is going. So the opposite direction, we can put equivalent force to cancel it. Clear? That's why I did this one. You have a look at home. It is not a difficult thing at all, but it will help you. All right. And now, quickly, I show you a small thing, around 2-3 minutes, and then we'll go home for today. The part 3. So part 2, I'll be uploading it in your canvas today. You download it immediately. Now it's instantaneous center of zero velocity. Now, young people, instantaneous center of zero velocity method, it is only valid for velocity. You cannot use it for acceleration. You cannot use it for acceleration. And also, you cannot use it for straight line motion. Straight line motion, it is not valid. It is only for rotational motion about a fixed point or fixed axis or general plane motion. Remember, our motion can have 3 types. The translational motion, rotational motion about a fixed point or fixed axis, general plane motion. And general plane motion, it is a combination of curvilinear translational motion plus rotational motion. So, usually, it is then you can say, okay, as we cannot use it for acceleration, why do we need it? Because we know only upper. It is only for velocity, but it allows us sometimes complex problem to solve velocity very quickly. That is the engineering advancement or engineering benefit. That's how we do it. Again, remember that if anyone asks you that the instantaneous center of zero velocity method we can only use for velocity, and we will not all velocity. The links that have motion, the rotational motion or general plane motion, complex motion, then we can use, not for translational motion. But on the other hand, we cannot use it for acceleration. So why the damn we need it? A very good question. If someone tell you that why Professor Firoz you need it, because your hands are already tight. You cannot use 1/3 of the motion, which is a translational motion, and then you cannot use for acceleration entirely. The reason is, this allows us in many engineering applications to find the velocity very quickly. How complex the problem is, it doesn't matter. Very, very quickly. That is one of the reasons why we learned this method. So I wrote all this beautiful thing for you. You can read it at home, not a problem. But basic thing I show you one with an example. That is also you can see it at home. With this slide, I will stop for today. Now, you learn that things in your engineering dynamics, but by this time, like me, I also forget a lot of things. On the other day, I could not remember one of my very close friends' name. It was so embarrassing. It is because I showed you yesterday the graph. Remember that? Some of you thought I was joking. Actually, I am not joking. I am actually showing these things. But our memory is going with the age, but our analytical power is going up. That's why I forgot my friend's name. All right. Now, if you, I know many of you know how to ride bicycle. Some of you may not know, but bicycle riding is a big fun. In a bicycle, it has usually two wheels. So there was a one wheel as well bicycle, but I never tried it. In a very broad daylight, during the daytime, sunny day, and road surface is not wet like today, very dry, no oil, no water. In those conditions, if you are standing some location and you are looking at the bicycle wheel, you know, someone riding bicycle and you are standing, like me, you are standing and you see someone is going and you are looking at the wheel, not the person, wheel. If sunny day, road surface is absolutely dry, no oil, no water, nothing. In those cases, you will see if you are standing in the correct location. I saw many times when I was a child, but I did not understand it at the time what's going on. I thought it's an act of God. What is that? You'll see the wheel, say bicycle is moving that way, so our wheel is rotating clockwise. And you will see this when this wheel come into contact at the road surface, in this section, all the spoke you can clearly see. But if you look at on the top section of the wheel, it does not clearly visible, looks like some hazy. We call blurry. It's hazy. You cannot see spoke clearly. But when same wheel, when it come into contact with the road surface at that contact point here, at that time you can see the spoke. You know spoke, a lot of spoke. What is going on? I said yesterday that our rigid body is absolutely solid, it cannot deform. On the other hand, it cannot have that our wheel at the when it is coming to the close to the contact point, it is slowing down. On the other hand, on the top section, it is moving faster. It cannot be, because if it is, then it will be twisted. Because every section of the wheel will be same rotational velocity. Is it clear to everyone? So what is going on? Why? We can see the spoke at the bottom where it come into contact with the road surface. Clearly we can see with our naked eyes. And top section we cannot see. What is happening, I explain to you. When our wheel is coming into contact, our road surface is little bit rough. Even on this one also rough. It is not absolutely smooth. There is a spike. If you do under the optical microscope or electron microscope, you can see a lot of waves is coming here. So road surface is like that. Look at here. Like that. Because a lot of stone and a lot of other things. So when our wheel is coming into contact, this spike and this one actually hold them together. That's what we call friction force. So if momentarily our wheel did not stop at that point, there will be slip. If slips occur, we will not be able to move forward. At that contact point, it will be rotating the wheel. Clear to everyone? So what happens? I said no wet condition, no oily condition of the road surface. It means all these spikes are there. When our wheel is coming into contact at that point, it momentarily stops because of the friction force. And when one fraction of a second, even not a 1 second, and when momentarily stops, our beautiful eyes immediately pick up that moment. And because of that, we can also see the spoke clearly visible. And momentarily stop and we're moving forward. Clear to everyone? Coming the next one. Coming the next spoke. Coming because our wheel is rotating. That's why on the only in this section we can see our spoke clearly visible. On the top section it still looks like it is a motion. But it is done, it is being done so fraction of a second, it does not have time to deform our wheel. Clear to everyone? And now, why it is happening? As momentarily it is stopped at that point, no slips occur. We can consider it is an instantaneous center of zero velocity. It means that there is no relative velocity at that point. Clear to everyone? And that beautiful point, when we can show that there is no slips occur at that point, no relative velocity at any joint point, no relative velocity, that point is considered automatically instantaneous center of zero velocity. Clear to everyone? And that point we will be using in our instantaneous center concept tomorrow. We will be using, I'll be telling all this beautiful thing, and then we move on to our more in-depth understanding. Clear? And I'll show you, because of that momentarily stop and velocity approximately zero, it is not exactly zero, approximately, hey, remember young people, I said it momentarily stops. Momentarily stops. It is not fully stopped, because nowhere in the world, when the wheel is coming into contact with the road surface, there will be a small tiny fraction of slip. And that's why, young people, I wrote that point be approximately zero, not absolutely zero. I did not put an absolute sign. Clear? Can you say that? And that is more than enough for us, engineering solution. Because our engineering solution, whatever we get, even normal case we multiply 25% safety factor, 0.25. And when something you design, if it fails, there will be huge human losses. There we multiply by 300 percent. Aircraft longeron, which is coming from aircraft wing with the fuselage, we reinforce it 5 times. So therefore no error. Error cannot, because of error, this system will not fail. Clear? Okay, with this I stop here, young people.